Okay, so once again, so what is statistics? Everybody can read this. Should I make it bigger? Make it bigger, okay. Let's see if I make it slideshow. That's better. Okay, so what is statistics? Well, like I said, I just say in a word that it's the science of data. So it's the science of investigating data and uncertainty. So statistics deals with, first of all, design of data collection. So what are the methods that you can apply to collect data? That's the design of data collection. And then it also deals with organizing, summarizing, and presenting data. So that means, again, you are looking at methods for organizing, summarizing, and presenting data. So usually these are, when we look at the presentations, they will be usually graphical or tabular. Okay. And also it deals with analysis, interpretation of data, and making conclusions from data or inferences from data. Okay. So the first part is basically how you should be collecting data. The second one is how you should be organizing your data so that the data makes sense to you. And then third, once you understand your data, then you do some analysis on it to accomplish whatever goal you have in mind. So statistics has three main areas. So one is design, another is descriptive statistics, and the last one is the inferential statistics. Once again, design, this area is concerned with designing statistical studies. So for example, designing surveys and designing experiments. We talked about designing surveys a little bit in the first class. For example, how you should create a survey in order to study presidential elections and to understand the voter preference, for example, and then designing experiments. Well, for example, clinical studies, they do a lot of experiments to collect data. Okay? So how effective a medicine is, for example, in order to study that, you would use experiments to collect data. Now, descriptive statistics in this area is concerned with organization, summarization, and presentation of data. So basically we have the graphical methods and numerical methods, or you can say tabular methods to do that. Inferential statistics, so that's where you are trying to draw. This area is concerned with drawing conclusions or inferences, and what we will see is that some examples of that would be estimating population parameters and the test of hypothesis. Okay. Estimation of population parameters, for example, let's say I am looking at the weight of ONU students and I want to know what's the mean weight or the average weight of ONU students, right? So if I think of ONU students as my population, assuming that the population is so big that I cannot really look at every single person's weight, so I take a sample of say 200 students and then look at their weights and then use the sample average weight to estimate the population average weight. So that's what we mean by saying when we say estimation of population parameters. And test of hypothesis, let's say that 10 years ago, the president of ONU claimed that 10 years from now, which is today, the average weight of ONU students will go up significantly. And he may have claimed that because of how bad the cafeteria is, right? So now today we need to test his claim, right? So that's the sort of things that you look at when you talk about test of hypothesis. And these things will be more clear later. One thing that I would want to say though is that we will not be concerned with design part of this diagram. Okay? If you ever are interested in the design of surveys and experiments, there is a course on it. And if you ever think that when you go to work you need to do something like that, then that's the course that you want to take. Okay. There is a very important concept in statistics which is variable. So in statistics, we study certain traits or characteristics of certain objects or individuals. And the traits or characteristics are called variables, and the individuals or objects are called units. So let's go back to the example of weight of ONU students, right? In that example, what are the units? The units are the students at ONU. Okay, those are the individuals of interest, right? And what's the variable in that example? Well, what trait or what characteristic are we studying in that example? Well, we are studying the weight, right? We are studying the weight of each student, right? So in that case, weight is the variable. Is that making sense? So some other examples, so units could be students, and then some variables for these units could be GPA, height, weight, number of hours spent on internet, number of hours spent on Facebook, whatever you're trying to study about the units, right? And units could be library books. So you may be looking at you may look at variables like replacement costs for the books, frequency of checkout, and repairs needed, and so on. If you have a manufacturing plant, and let's say you are manufacturing chips, computer chips, then one of the characteristics that you may be interested in is defectiveness. So whether or not a chip has defects or not. Is that making sense? Descriptive statistics is the study of graphical and numerical methods that are used for describing data in a manner that shows the essential features of the data. So you need to organize your data, summarize or present your data in such a way so that it shows you the essential features of the data. Okay. So in descriptive statistics, once again, you are concerned with organizing, summarizing, and presenting data. Okay. Inferential statistics, that's the study of methods that are used for analysis of sample data and making inferences about a population. So like I said, when you study, for example, voter preference in a presidential election, right? There are many voters, right? It's a finite number of voters, but there are millions of voters. One way you can go about it is by asking every single voter what their preference is, right? And then do your calculations based on that. However, you better have a whole lot of money to do that, right? So usually you don't do that. What do? Well, you probably take a sample of 1,500 voters, right? And then you do some calculations based on the sample of 1,500 voters, and then you use that to say something about the preference of the entire collection of the voters. Is that making sense? So from data, you would like to estimate, predict, or decide about whatever characteristics that you are studying of the corresponding population. The population of units versus the statistical population. So these are two different concepts. We understand what units is, right? When we look at, if I am studying the weights of ONU students, then ONU students will be the units, right? So population of units means entire set of all units, right? That's the population of units. It's the set of all objects or individuals of interest or concern, right? Now, what is the statistical population? A statistical population, or sometimes just called the population, is the collection of measurements of certain characteristics measured for all the units. Okay? So imagine that my population of units is the population of ONU students. For every single student, imagine that I have the measurement of his weight. So for each student, there is a measurement of weight, right? So if you look at the collection of all measurements of weights of all the students at ONU, that's your population or the statistical population. Does that make sense? Is everybody clear on the difference between the population of units versus the statistical population? Right? You're looking at the units or the objects versus whatever measurements you are doing for each object or an individual, right? Is that making sense? Again, a sample is a subset of the population that is collected for an investigation. When I say it is a subset of the population, remember when I say just the population, it is the population of measurements. So it is the statistical population, not the population of units. So when I say a sample is a subset of the population, I'm saying it's a subset of the collection of measurements. Right? I have entire collection of individuals or objects, then I have the corresponding entire collection of measurements, and from that collection of measurements you take a subset, that's the sample. Now it is important that a sample is representative of the population, and second, it's important that the sample is not systematically biased. Okay? Therefore, we must use randomization in selecting a sample. So when I say representative of the population, what do I mean? Well, if you are looking at voter preference in an election, right? In an election, let's say we are looking at Ohio voters. And if I take my sample of 1,500 voters solely from Ada, is that a good way of, is that going to be representative of Ohio? No. If I take my entire sample from Cleveland, is that going to be representative of the entire Ohio? So that's what we mean when we say that the sample must represent the population, and it better not be systematically biased as well. Okay, so population sample, once again, you have a target population and you're picking a subset of that. Now, even though I have people here, imagine that each object or individual here has a corresponding measurement. So when I'm picking a sample, I'm picking a subset of measurements. Okay, so in order to select the sample, a lot of the times we use a random number table. And what is a random number table? A random number table looks like this. Even though we have the numbers written 5 at a time and separated, when the computer really generates this, there are no gaps. Okay, it's just generating digits after digits. Okay. So the reason you see gaps here so that it's readable. Okay. So what is a random number table? So what we would like it to do is that when I want to say I have how many, maybe I have here, I don't know, maybe 30 students here. Let's say I want to pick 5 students at random from this class, right? And so what I can do is, one way I could do it is I can write down the name of each student on a piece of paper and then put them in a bowl and then juggle them around and then pick 5 people at random, right? Just like you probably do lottery tickets, right? So that's like I'm trying to pick somebody at random so that I don't have any bias when I am picking it, right? So when I'm picking a student, usually I might be picking somebody from the front row because that's just easy to do, right? Or another way I could do it is that I can assign each one of you a number. Let's say the last 2 digits of your ID. And then I can start reading. I can randomly pick any place in this table. Let's say I pick this. And then I can start reading 2 digits at a time because remember I assigned you a 2-digit ID. So I can read 2 digits at a time. I can go along a column or I can go along a row. So I can read 95, then 70, then 51, then 07, then 22, then 72, 47, 40, 14, 34, and so on. So whenever I find a match with one of your ID, I pick that person. Is that making sense? So we use the random number table to pick a random sample. Does everybody understand that? Now, what's the property of this random number table? Well, what we would like is the following. We would like the computer to generate this table as if whenever it is generating a digit, every single digit is equally likely to be generated. Every time it generates a digit, any of the digits is 0 to 9, any of those digits is equally likely to be picked or generated. All right? That's what you want ideally from the computer. However, those of you in computer science, there is one or two people here, right? Is that possible really? Can a computer generate random digits? Not quite. Because remember, at the end of the day, the computer has to follow some instructions to do that, right? So anytime you're following some instructions, right, you're following a systematic way of doing something, right? And so therefore, there can never be a truly randomized table like this. However, a computer can generate something close to it. Let me just say that. Something good enough that for practical purposes, it is random. Am I making sense? So for applications and practical purposes, there is a way of generating somewhat random tables, okay? Everybody is okay with that? In my last spring, I taught number theory with cryptography applications, and in that course, we go into more detail about these random number generators and stuff. But we're not going to go there. Okay, so the sum of the properties of a random number table. A random number table is a table of random digits, whatever random means. Okay. One of the quotes that I don't remember exactly, but it says as if that a sequence of something is some numbers is random. It's just that we don't know what exactly randomness means. Okay. So again, randomness, when you think about it, just think about in the following way, that if I am picking 5 people from this class, whatever method I'm following to pick the students, every time I pick a student, I want to make sure that any of you is equally likely to be picked. Okay? So that there is no bias. Okay? If I just pick everybody from the front row, there is a bias, right? It is a list of 10 digits, 0 through 9, having the following properties. The digit in any position in the list has the same chance of being any of the digits from 0 to 9, which is what I said. The digits in different positions are independent. The digits in different positions are independent. What it means is that the value of one has no influence on the value of any other. Also, any pair of digits has the same chance of being any of the 100 possible pairs of digits. Right? There is a, you guys get that there is a total of 100 two-digit numbers, right? Starting with 00. So any pair of digits has the same chance of being any of the 100 possible pairs, and any triple of digits has the same chance of being any of the 1,000 possible triples, and so on. Those are the ideal properties that we want the table to have. However, like I said, it's not quite possible. Okay. Let's do an example. Let's say 80 pumps were manufactured last week. Select a sample of size 5 to test for possible defects before they are sent to the buyer or the purchaser. So you're trying to select a sample of 5 pumps from 80 pumps. So one way of doing it is what? One way you could do it is you can label the pumps, 80 pumps, right? You can label the 80 pumps from, sorry. Okay, so you can go ahead and label the 80 pumps from 01 to 80, right? 01 up to 80, label them. And then in order to pick your random sample of 5 pumps, what you do, well, you can go to the table of the random, you can go to the random number table. Remember, you labeled, okay, somebody help me by writing the numbers down, okay? So let's just pick randomly someplace. So I'm going to close my eyes, I'm going to put my finger somewhere. Okay, 44, let's say. And then from 44, do you want to go horizontally or you want to read them vertically? Let's do vertically. 2 digits at a time. So 44. So my first pump in my sample would be number 44. 85, well, that's outside of the numbers that I assigned, so 85 will be ignored. 65, so I found the second one. 05, the fifth one. 46. So how many do I have so far? 4. And 12. So those are the 5 pumps that I'm going to pick them. So anytime you have a number which is not one of the assigned numbers, you just ignore that and then keep reading it, the table. Is that making sense? Okay. You have to understand the difference between what a parameter is versus what a statistic is. Note that this is not statistics, right? This is a statistic. A parameter is a descriptive measure of a population. So this is a quantity calculated based on the entire population of measurements. A statistic is a descriptive measure of a sample. So what it means is that it's a quantity calculated based on the measurements in a sample. For example, let's go back to the example of weights of ONU students. So what I want to calculate, what I want to know is what's the mean or average weight of ONU students, okay? And in order to do that, let's say I pick a sample of 200 students, right? So imagine that you can calculate the average weight of all the ONU students, right? So there is a true average weight of all ONU students, right? So that's the population parameter. Versus the statistic would be whatever average weight I calculate from the sample of 200 students. So I pick 200 students, I measure their weights, right? And then I take the average of the 200 measurements that I have taken, right? That average, that sample average, that's a statistic. Is that making sense? Is everybody clear between the two differences? There is so another example would be voter preference in a presidential election, right? There is a voter preference would mean, let's say we are looking at what percent of voters prefer Trump, let's say, okay? There is a true voter preference, right? There is, let's say, the true voter preference at this moment is, let's say, 46%. Okay? So there is a true one. Usually we don't really know what the true one is, but you can imagine there is a true voter preference, right? 46% would vote for Trump, let's say. But when you're trying to estimate the population parameter by using a sample statistic. So you take a sample of 1,500 voters, and then you measure the voter preference based on the sample. Let's say from the sample you found that 48% of the sampled voters prefer Trump. Is that making sense? So that 48% is a statistic, right? Versus there is a true voter preference, right? Everybody's clear? So parameter versus statistic. Parameter is based on the entire collection of measurements, right? Statistic is based on only the measurements in a sample. Okay. So once again, you have a sample which is a subset of the population of measurements. A statistic approximate the corresponding parameter of the population. So usually you are trying to say something about the population parameter, right? You're trying to estimate or say something about the population parameter, and you're using the sample statistic to do that. So sample statistic is a estimate of the population parameter. So when I write X bar, I mean, for example, average weight. Let's say X means weight. Let's say then X bar would be average weight of a sample, from a sample, and then mu here represents the mean or average of the entire population. Everybody is looking at the clock. Is that, am I out of time? What's the time? What's the time right now? Okay, it's 10:49 now. So yeah, we are almost, I think that's probably 3 minutes slower. Well, this is probably a good time to stop as well. If you want to read ahead the rest of the slides, you can find them in Moodle. Otherwise, I'll see you on Friday.